Section 4.1 is applications of the first derivative. So we're starting off on a new chapter here. Everything we do in chapter 4 is going to be some sort of an application of the derivative rules that you learned in chapter 3. So we're going to be using all those rules and applying them to actually solving problems. Now, they might not always be like, traditional application word problems like you're expecting. They might just be calculus applications where you're just trying to find information about a graph. So that's mostly what we're going to be focusing on. In this section, we're going to be focusing on looking at where the graph is increasing or decreasing and finding maximum and minimum values. So we're going to use the first derivative to find where the function's increasing, decreasing, and locations of relative extrema. So relative extrema just means like, where do you have extreme values? So a maximum or a minimum. I mean, you can think about extreme values in your life as maybe extreme temperatures. So how high the temperature gets or how low, you could think about that as a graph as you look at those values throughout the year, for instance. And then we'll talk about how the graph of a derivative function relates back to the graph of the original function. So lots of really, really, really important stuff today. Really important. I can't emphasize it enough. Section 4.1 and everything that we're going to be doing right now is laying the foundation for the rest of this chapter. And everything you did in chapter 3 was laying the foundation to get started with this. This is crucially important. Put on your game face and be prepared to really get into this because it's crucially important to you. We're going to be using these applications, by the way, again in chapter 5 as we apply our derivative rules to different types of functions like exponential and log functions. So we're going to be looking at these applications in chapter 4 using derivative rules from chapter 3. Looking ahead to chapter 5, you're going to be combining everything you learned about derivative rules in chapter 3 with applications in chapter 4 to new types of functions for exponential and logarithms. Got it? All right, that's the plan. All right, applications of the first derivative. By the way, I was using these last night with my Calc 3 class. They're not going anywhere. So if you plan to take any more math after this that's anywhere near calculus based, this whole idea is going to be part of your life now. This is part of your life. So be prepared to accept it and love it. All right. Where are the minimums and maximums in a local neighborhood, i.e. the peaks and valleys? These are called relative or local extrema. So we're going to determine what the value of the derivative is at these points. So looking at the graph, for instance, for number 1, you can find relative max and relative min. So when I'm talking about a neighborhood, I'm not talking about looking at the entire graph. So if I'm talking about a local neighborhood, I'm just trying to narrow in on a specific point. I mean, think about what it means to be in your neighborhood. Like, for instance, if you live in Elgin, that's a very broad area, but your neighborhood is a very small part of Elgin. So when I'm talking about a neighborhood, I would be zeroing in on like, okay, where do you live in Elgin? Because it doesn't make sense to talk about you live in Elgin. Okay, well, that's a very large place. So zeroing in on that neighborhood gives you a little bit more information. So when I'm zeroing in on a local neighborhood, what I'm doing is I'm basically just isolating a specific portion of the graph that usually contains maybe a piece of the graph that's going to be more important to us, like in this particular instance, a maximum or minimum value. So I can look at that in a local neighborhood by just focusing on a specific place on the graph. So right now I'm going to focus on the neighborhood that's sitting around x equals 1. So if I'm looking at the neighborhood around x equals 1, I can say that we have this relative maximum value that appears to be occurring here at x equals 1. Did I say -1? I don't think so, but either way. So this will be a relative or local max. It does not matter to me which one you call it. A lot of times we just say we have a relative max. You can say maximum or you can say max. It does not matter to me. Now, if I looked at a different neighborhood, maybe around x equals 2 in this instance, I would be able to find a local minimum. I know that my relative minimum must be this place where I have the smallest value in that area. So I'm just focusing in on like what happens in this area. Now, you might be wondering like, well, what if we looked to the right of 2 and this graph keeps going up? Wouldn't I say that this is a relative max? No. the idea is you have to be able to find values on both sides of this point in order to say it's a maximum. So in order to say you're at the top of a hill, you need to know that there's something on the other side of the hill that's going back down. You can't say you're at the top of the hill here because you don't know. It might keep going up. It might just stop there and you don't know what's going on. So in order to say you're at the top of a hill, you have to be able to see what's on the other side. So in this case, if you're thinking about these as peaks and valleys, or hills and valleys, however you want to think about it, I cannot say that this is a relative maximum. Just how I can't say that this left edge of the graph here where the curve seems to start is a relative minimum. I don't know that because I don't see anything that's happening on the other side. And I need to be able to have points on both sides so that I can indicate that this value is the absolute largest or the absolute smallest. So in this case, I can make a statement, though, about what's occurring at these two values of x. I know that when x is 1, I have a relative maximum. And we've sort of been leading into this idea for a while. But when you have a maximum value, you get to this place where the slope of the tangent line is 0 because it's horizontal. The slope of a horizontal line is 0. Same idea with the minimum. When you're at the minimum, the slopes of the tangent lines to the left of that value are heading downwards. They're decreasing. Then you hit the minimum and the slope of the tangent line is horizontal. It zeroes out. And then as you move to the right of 2 to values that are larger than 2, now you're seeing these positive slopes for the tangent lines. So what we're looking for here is that at the place where you have a relative maximum or minimum, the tangent lines went from either positive to negative or negative to positive regarding their slopes. But we can go ahead and say that f prime of 1 must be equal to 0 because remember that f prime is the slope at x equals 1. And we can say the same thing about what's happening at x equals 2. So we can say that f prime of 2 equals 0 because, again, we're seeing that when x equals 2, the slope of the tangent line is 0. Now, the whole idea here of going through this and talking about it is that I'm going to be giving you functions today, and you're going to have to decide, you're going to have to figure out just by looking at the numbers where you have the slopes of the tangent lines changing. So where might you have a place where the slope of the tangent line is 0? And then you're going to have to figure out what those values of x are to determine, like, do I have a relative max or relative min, or maybe neither. So that's what we're going to be doing in a couple minutes. The other thing that you might see when we're talking about peaks and valleys is this situation that you see in example 2, where you have this sharp point on the graph. Now, it still represents a relative minimum. The problem is that the derivative doesn't exist at sharp points. So we talked about that in the previous chapter. A function is not differentiable whenever there's a sharp point. So that we would say in this case, let's say we called this function g of x. We could say that g prime of 1 does not exist. And that's because we have the sharp point on the graph. So we still have a relative minimum in that case, but it's just a case where the derivative does not exist. So these two examples both illustrate the same idea, just in different ways. So it might be the case that we have a slope of the tangent line being 0, or it might be the case that the slope of the tangent line doesn't exist at that point. And if you'll remember, you could show this using limits. We didn't really focus a whole lot on that in this class. But if you wouldn't be able to actually get, you would not actually be able to get a slope of the tangent lines here because really this looks, it almost sort of looks even like a piecewise function. But as you follow this on the left, your tangent lines would be heading down like this, whereas on the right, your tangent lines look like that. So you don't have a situation where we just have this one tangent line. All right, so your observation is relative or local extrema occur at points where the derivative equals 0 or the derivative does not exist. We'll put that down here. They occur at points where the derivative equals 0, or it does not exist. Okay, so that's sort of the takeaway from looking at these graphs. Now we can make, or we can give some terminology to this. Like, what does this actually mean? If the derivative equals 0, what do we call a place like that? Well, that's what we call a critical number. So critical numbers are points on f of x, or whatever your function is, where f prime of x equals 0, or f prime of x does not exist. Now, we need to make a really important distinction here, because I think that the does not exist part tends to be really confusing for students, because a lot of the time when you end up getting a derivative not exist, it's not because you have a sharp point. A lot of the time it's because you end up having a vertical asymptote at that location. So we need to make a distinction. So I'll say note, vertical asymptotes are not considered critical numbers. Vertical asymptotes, we usually just abbreviate these with VA, are not considered critical numbers. I mean, think about what happens when you have a vertical asymptote. I'm going to give you an example using one in a couple minutes here, but when you have a vertical asymptote, how could you possibly have a max or min at that location? You don't have a point at that location. The whole idea of a vertical asymptote is that your function's not defined there. So we're going to make sure that we still think about the fact that we have vertical asymptotes when it happens. We do need to consider them, but we don't officially say that they're critical numbers because they can't possibly yield maximum or minimum values. Okay, so what can we say about the value of the derivative on these intervals? So now we're going to really be getting into this idea of, like, how might I know whether my graph is increasing or decreasing on an interval? Well, what we would do is we would find places where we had critical numbers. Like this is, for instance, that graph that you had for the same exact graph you had for number 1 above. So we would say now, like, all right, we've got a critical number at x equals 1 and a critical number at x equals 2. And what we're going to be doing is we're going to be focusing on what happens to the slopes of the tangent lines to the left of 1, between 1 and 2, and then to the right of 2. So if I'm looking at the slopes of the tangent lines, as I'm looking at values to the left of 1, any point value that I chose here will have tangent lines that are positive. They're increasing as I move from left to right. Sorry, they're a little bit hard to see. Maybe I did not choose the best color here. But I would say that f prime of x at this location is positive, because all of the slopes of the tangent lines are positive until I get to 1. Now we're going to assume, maybe I should have put an arrow on this graph just indicating that this behavior will continue. Oh, I didn't mean to write y. Why did I do that? Oh, she does weird things sometimes. Here we go. When it works great. And then I mess it up somehow and it just does not want to work. Okay. Excellent. So we can go ahead and state now that it must be the case that f prime of x, the slopes of the tangent lines, the derivatives, are positive until we hit this critical number. Now, of course, at the critical number, we end up with that 0 slope where the graph levels out. But up until I hit x equals 1, I can say that f prime of x is positive. It must be, because the slopes of the tangent lines are all going up from left to right. Now, that's going to change, however, as I move between 1 and 2. So the slope is going to 0 out at 1. And then as I move to points between 1 and 2, well, now you're getting that these tangent lines start to head down from left to right. So all these slopes of the tangent lines are heading downward. So here, I would say that f prime of x is less than 0. The slopes are all negative because they're all going down from left to right. I know. I'm taking something that you probably would have had a very intuitive feel for and making it complicated by talking about derivatives. But we need to make this connection. It's really important. And then again, as I move to values that are to the right of 2, I'm getting all these tangent lines that have positive slopes. They're going up from left to right. So I would say that in this case, f prime of x is positive. So we can use our interval notation to state this. So what we would say here is that we have values where f, our function f, let's name it f of x will be our function. So we can say f is increasing or f is decreasing, and we're going to list these as intervals. So f is increasing from negative infinity. We're thinking about this in terms of x values. So officially, I guess I should be looking at it this way. I know it doesn't really look like the graph is going all the way over here, but it doesn't matter. Technically, it could. From negative infinity all the way up to 1, but it's not increasing at 1. So I'm not going to include 1 in this interval. So I'm going to say that the graph is increasing from negative infinity up to 1, and then it stops increasing and it goes to 0. Now f starts to decrease between 1 and 2. And then after 2, not at 2, because at 2 it's constant, it starts to increase again. So I'm going to say that from 2 to infinity, the graph is increasing. And that's how we would write this. So later on, I'm going to be giving you some examples where I'm giving you functions, and we're going to be finding derivatives, and we're going to be looking at places where the derivative is positive or the derivative is negative, and we're going to be making these conclusions about where the function might be increasing or decreasing based on what's happening between the critical numbers. In order to do that, we'll need to determine what the critical numbers are, and that will be where the slope or the derivative is equal to 0, or in the case of example 2, does not exist. So we can do the same thing here with example 2. We called this graph g of x in the previous example. We'll call it g of x here. I want to just put like a little arrow on this so that you can sort of tell what's happening with the graph. We'll just assume that it keeps increasing. You know what? I want to make the arrow go a little bit more up because I don't want you to think that this is like a local maximum. Oh, I have messed up the whiteout pen. It needs like a reset. Okay. But let's just say I put an arrow on it just to indicate that it's maybe continuing to go up and to the left. All right, so we already said we had a critical number here. So this would be the critical number where the derivative does not exist. It does not mean that the slope of the tangent line in this case is 0. It just means that your derivative does not exist. Now, as you move from left to right on your curve, you're heading from values that are less than 1 up to 1. The slopes of the tangent lines here are going down from left to right. So in this case, we would say that f prime of x is less than 0. As you move towards values that are greater than 1, or move past 1, all the slopes of these tangent lines, this appears to just be linear, are going to go up from left to right. So we would say here that f prime of x is greater than 0. So the slopes are positive because the tangent lines are going up from left to right. So again, we can make this, we can make a little, not a table, but we can summarize this information below just by saying that g is decreasing, and we're going to assume it just continues this behavior where it goes up and to the left. So we'll say it's decreasing from negative infinity all the way up to 1. And remember, we're not going to include 1 because at 1, it's not decreasing or increasing. It's neither. It's constant. And then we could say that g is increasing from 1 to infinity. And at 1, it's doing neither. It's neither increasing nor decreasing. All right, so observation, where a function is increasing, its derivative is positive. And where a function is decreasing, its derivative is negative. All right. Now, another observation is that not all critical numbers will be relative extrema. You're going to come across this pretty often when you're dealing with polynomials and rational functions. This graph, sorry, I know it's a little bit hard to read, but you have it on your notes. It says y equals x cubed. Well, if y equals x cubed, y prime is 3x squared. Now, its derivative equals 0 when x equals 0. But when x equals 0, you're seeing here that, yes, the graph technically has a horizontal tangent line at this point, but it's increasing to the left of x equals 0 and to the right of x equals 0. So we can't say that we have relative extrema because we actually don't. So we would say we have no relative extrema. So we don't have any local maximums or minimums because f prime of x is always positive. F prime of x is greater than 0 on both sides of the critical number. And the critical number is, of course, x equals 0. So if you look to the left of 0, you'll see that the slopes of the tangent lines are heading up from left to right. But if you look to the right of 0, you'll see the same thing. So they're increasing everywhere except at the critical number, at which point they zero out. The slope is 0. So yes, technically x equals 0 is still a critical number because the derivative is still 0 there, but it does not matter. It does not yield any relative extrema. All right, so pulling together all of our observations, I know this is a lot to get you started with, but it's all the background information that you're going to need to set you up for these examples. We have the first derivative test. Okay, so to find intervals where f of x is increasing or decreasing and to find local extrema, we're going to use the first derivative test. That means what we're going to do is find critical points of f of x by finding where f prime of x equals 0 or does not exist. And we're going to perform sign analysis. You know, I am going to see real quick if I can fix my focus. I did this before I started and I thought the focus was great, but now I don't know, sometimes it's like a lighting issue and then it changes. I just want to see if I can a little better. Too much. Let's try that and see. I don't know. It seems like if I do a manual focus, it's always better. We're going to perform sign analysis using the critical points obtained from number 1 as shown, or I'm going to give you an arbitrary example of what this would look like. So this is not applying it to any particular function. I just want to show you what a sign analysis would look like. So what you're going to do is you're going to find those critical points where your derivative either equals 0 or does not exist. And you're going to list them in order as though you were on a number line. So maybe this would be like your critical point number 1, or sorry, we're calling them critical point, critical number, they're the same. So don't be like, wait, is it a critical point or a critical number? Every textbook has their own convention, and we math teachers teach calc a lot, and we just kind of use the same terminology or different terminology, because we're used to just calling them critical points or critical numbers. It does not matter. You pick what you want to call it. So let's say that I had a critical point here, a critical point here, and then another one to the right of that. Now, what we would be doing is performing sign analysis. So we'd be evaluating what's happening with the function or with the derivative between these critical points. So I might have a situation where, for instance, I had f prime of x being positive and maybe f prime of x being negative, positive, and positive. These are just going to be arbitrary test values that we place in between the critical points. So this would be a sign analysis using f prime. So this might be like f prime of x is positive, or like f prime of x is negative, so on and so forth. If we had that, well, we know that when f prime of x is positive, we know that the function is increasing. We know that when f prime of x is negative, it means the function's decreasing. So maybe I'll say f prime of x equals positive and positive. So that means on this interval, I'd be increasing. And then on the last interval, I'd also be increasing. So something like this. Now, you could make a conclusion if your function went from increasing to decreasing. That means that your derivative or your slopes went from positive to negative. In between there, you had a critical number. So you could make a conclusion at that point that this critical number, CP1, represents the x value for a relative max. Now, you can eyeball this too. I mean, the nice thing about sign analysis, I really just feel like it doesn't exactly tell you what's happening with the graph, but it gives you a good indication. You know that the graph is increasing until you get to this critical point, and then it's decreasing. You don't know how sharply it's increasing or how sharply it's decreasing, but you know that it's got some hill here at the critical point number 1. So your relative max would be at critical point 1 and then f of critical point 1. So just the function value at that point. Now, in the case of critical point 2, your function went from decreasing to increasing. You can see here now that you hit this valley, you hit a low point, and then at the critical point, you must have a 0 slope, and then it starts to increase again. This means that you have a relative min at CP2, f of CP2. And usually when we list minimum and maximums, we just list them as ordered pairs. Now, as far as CP3, this is a situation that you saw in this example at the top. So the slopes of the tangent lines were increasing to the left of the critical number and to the right of the critical number. So yeah, a critical number does indicate that at some point you had a 0 slope. It just means that you hit the 0 slope and then it just kept going up. So there's no relative extrema here. So no relative extrema at CP3. Okay, so kind of depending on the type of function that you're looking at, you might have a lot of places where you have critical numbers, or you might just have one. Sometimes we have none, and you just have to pick like a test point. But all the values that you're choosing inside these intervals are just arbitrary values that you're testing that belong somewhere inside that interval. Now, if you're just like, what the heck is going on? I don't know what this means. I'm going to show you some examples, and you're going to get used to doing this, and everything will be just fine. You'll get to be very good at doing analysis. So what we're going to do here, here's the meat and potatoes of this. Find the intervals of increasing and decreasing and the relative extrema. So we're going to go ahead and look at a function. In this case, I'm going to give you a polynomial function. Trying to figure out what color I want to be married to for the next several minutes. This one. So this will be example 1. The function will be a polynomial. Now, I find that this is easiest to do with polynomials. So we usually start out talking about polynomials here. So this will be 3x to the 4th minus 8x cubed plus 6x squared plus 2. Now, I want to remind you for a second, you maybe don't remember. So if I can jog your memory, back in college algebra or algebra 2, you learned to graph polynomial functions. And you did so by looking at turning points and by looking at x-intercepts. And let's see, what else did you do? You looked at possible like zeros. Oh, that was x-intercepts. Never mind. I'm thinking rational functions. But another thing you did was you plotted points by using a table of values. And like, let's say, for instance, you knew the graph was increasing and then you knew the graph eventually came back down again because the y values would start to get lower again. But you couldn't figure out where it actually, the highest point. You couldn't find the maximum or the minimum. And your teacher back in college algebra was like, well, just get as close as you can because you can only guess. The really cool thing about what we're doing here in calculus is there's no more guesswork. You're not just going to have to be like, I know it's going to come back down at some point. I just don't know where. You're going to be able to tell exactly where that maximum and minimum value occurs and what the maximum and minimum value might be. So it's a very, very powerful tool. We're going to put all this together when we do curve sketching, but later on in the chapter. All of this is laying the groundwork for you to just be able to sketch polynomial functions or rational functions or radical functions without having to use your calculator. Oh, I can't wait. It might be my favorite thing. I know I've said that so many times, but it's so cool. It's so cool. Just be like, I don't need my graphing calculator. I can graph this function on my own. It's very powerful. Anyway, I just gave you a polynomial function. In order to talk about intervals where the function's increasing or decreasing, or to find any relative extrema, the first thing I need to do is find critical points. So if I'm going to be finding critical points, I need to take the derivative. I'm going to find where the derivative either equals 0 or does not exist. Now, this is a polynomial function, so we're not going to get any like derivative does not exist stuff happening here. Polynomials are smooth continuous curves. But let's go ahead. We'll take this derivative. We'll get 12x cubed minus 24x squared plus 12x. And we're going to take the first derivative and set it equal to 0. We're going to use the first derivative test and perform some sign analysis here. Again, it's a polynomial. It's never going to have a derivative that does not exist. But we can at least find places where the first derivative equals 0. To do that, we're going to have to solve the polynomial equation. If you can factor it, do that. In this case, I have a GCF of 12x that I can factor out of each term. And that leaves me with x squared minus 2x plus 1 equals 0. And then we can further factor this. You're looking for two numbers that multiply to 1 and add to -2. And those values are x minus 1 and x minus 1 equals 0. You can always double check that. This is a perfect square trinomial, x squared minus 2x plus 1. Now, back in algebra, you would have said like, oh, wait, never mind. I'm thinking about something different. Hold on. Reverse that. Reverse the thought. My daughter would say delete. Okay, I'm going to go back to what we have here. You just took the derivative. You set it equal to 0. To find the critical points, you're going to solve for these values of x that cause your derivative to be 0. Now that means that we have 12x equals 0 or x minus 1 equals 0. And you have two factors of x minus 1. It doesn't matter. You're going to get the same critical number twice. All right, so you're going to have x equals 0 and x equals 1. Now remember, if this is 12x, it has a variable in it. We set it equal to 0. We solve and we get 0. If you just pulled out a GCF that was just 12 with no x in it, 12 doesn't equal 0. It doesn't, you don't use it. So that occasionally happens. Just wanted to remind you the reason we have to use this value is because there's an x in it. All right, so I have two critical numbers. Critical points, whatever you want to call them. Once you find the critical numbers, you can start to set up your sign analysis. So looking above, we're going to set up like a number line basically. And we're going to list our critical numbers in order from left to right. It's really important that we list them in order. So let's say here that I don't need to have a huge long number line, but I'm going to put some information in it. 0 we'll put right here, and x equals 1, maybe we'll put right there. What I'm going to do is I'm going to pick a test value inside each interval. Now you have 2 critical numbers. That means you have 3 intervals. Now a polynomial function has a domain of all real numbers. That means that whatever's happening to the left of 0 happens all the way down to negative infinity. And whatever happens to the right of 1 happens all the way to positive infinity. You're going to pick a test value that's usually pretty close to your number because you don't want to have some giant value that is hard to compute. So I'm going to pick a test value in the first interval. And I might say, let's let the test value be something like -1. And then my test value in the second interval, maybe we'll make a half. You can't find an integer between 0 and 1, so just pick a fraction, and I feel like 1/2 is the easiest fraction to choose. And then in the third interval, I would probably just pick 2 because it's close to 1, but it's greater than 1, so it's somewhere inside that interval. And what we're going to be doing here is evaluating the first derivative. That's why it's called the first derivative test. Find the critical points. We did that. Now we're going to perform sign analysis using the critical points as shown below. So I'm going to go ahead and use the first derivative test with my test points to determine what's happening on these intervals. So the idea is we know that the slope of the tangent line is 0 at x equals 0 and at x equals 1. If I pick a test point between negative infinity and 0, no matter what, the behavior should not be changing whether it's increasing or decreasing because it can only change that behavior at critical points. So if I pick a test value in the interval, whatever it's doing on that test value, it should be doing on the whole interval. So if it's increasing when x equals -1, it should be increasing all the way from negative infinity to 0. If it's decreasing at -1, it'll be decreasing all the way from negative infinity up to 0. Whatever it's doing at the test interval, it has to be doing the whole interval. So let's go ahead and evaluate the first derivative at each test point. And this will tell us something about the slopes of the tangent lines. Now, if you're just like, oh my gosh, I got to evaluate the first derivative at all these values, technically, yes, use your calculator though. I mean, if it's something like a polynomial, especially if you factored it, this will be a little bit easier to do. But in general, you're probably going to use your calculator. So, oh, I still have this example in here from yesterday. I'm going to go ahead and in my y equals, I'm just going to enter our derivative. Don't enter the original function. You're trying to evaluate the derivative. So my derivative was 12x cubed minus 24x squared plus 12x. I'm going to double check and triple check that I entered it correctly because all my information is based off of this. And then I'm going to go to the table. Now I have my table set to ask. Yours is probably also set to ask. If it's not, remember you go to second window to your table set and make sure your independent variable is set to ask. And then you go back to your table and just look at the values that you're interested in. The first value I want to look at is -1. The second value is +0.5. And the third value is 2. Now, when I look at these values in my table, f prime of -1 is -48. F prime of 1/2 is 1.5. And f prime of 2 is 24. Now, I don't care about what actual numbers you have here. The thing we're looking for is what is the sign of the derivative. The derivative is a slope. If the derivative is negative, that means the slope is negative. Because your first derivative was negative on the first interval, we know that your function must be decreasing on that interval. Because your first derivative was positive on that middle interval, you know your function must be increasing on the interval. And then we could say the same thing about interval 3. Your derivative's positive, the function's increasing. Now we can make some conclusions regarding that sign analysis we just did and how it relates to the graph of our function. If my graph is decreasing until I hit the critical number, and then after I hit the critical number, it's increasing, that means that I have a relative minimum at the bottom of this hill. So I have a relative minimum at 0, f of 0. The function value at 0 is the corresponding y value on the graph. Don't evaluate f prime of 0. It's a critical number. Its derivative will be 0 there. Don't do that. You're looking for the corresponding y value on your actual graph of the function. Now, you have another place where you have a critical number, and that's when x equals 1. But at x equals 1, your behavior does not change from increasing to decreasing or vice versa. Your graph is increasing, it levels out, and then it continues to increase. So that's like the example that we saw on the top of the page where the graph levels out, but it doesn't change its behavior. So we have no relative extrema at x equals 1. No relative extrema at x equals 1. Later on down the road, we'll want to plot that point just so that we know where it is on the graph, and it's going to help us to get a good picture. And that point would still be located at 1, f of 1. But in this case, we don't have to list it out because there's no relative extrema there. So to make a conclusion here, we still need to talk about finding intervals where the function's increasing or decreasing and talking about relative extrema. So my official answer is that f is, let's start with decreasing, I guess. F, my function, is decreasing on the interval from negative infinity all the way up to 0. Now, once I hit 0, the function starts to increase. I want you to be really careful here, though, when you list out the intervals for increasing, because what I often have students doing, and it's not correct, is they'll say, well, it's increasing from 0 to 1, and then it's increasing from 1 to infinity. So I'm just going to write the whole interval as increasing from 0 to infinity. And that's not correct, because this function isn't actually increasing at x equals 1. It levels out at x equals 1. It just for a split second in time has a horizontal tangent line, which means it's not increasing or decreasing at that point. So we could say that f is increasing on the interval from 0 to 1, and then we need to pick it up again at 1 and say that it's increasing from 1 to infinity. If you have a critical number that's splitting that interval, you can't possibly be increasing at that critical number. So it's really important that we get that right. This is 2 separate intervals. It needs to be written as 2 separate intervals. The other thing that you need to include in your answer is the value of the relative minimum. I sort of listed it here. You have a relative minimum at 0, f of 0. You need to figure out what f of 0 is. So for that, you're going to go back to your original function f. And if we're evaluating f of 0, well, 0, 0, 0 will be the values of the first 3 terms, and then plus 2. So f of 0 is 2. This is all the information that you need to include in your answer. So a lot just happened. There's a lot going on, but I think you'll sort of get into the groove. You find your critical numbers. I mean, it looks a lot like a lot when you get to the end of it, but I think the process is a very natural flow. You focus on taking the derivative, setting it equal to 0, or figuring out where it does not exist. You're getting those critical numbers, setting up your sign analysis, and making conclusions. Being able to make conclusions based off your data is the most important part. Well, I guess finding the derivative is also crucial, but you know what I'm saying. We should have that down by now. Also, we can't overlook the idea that we do have to solve these equations, which some of us haven't done in a while. So, okay, so that's a polynomial example. Those are usually the easiest ones to deal with. All right. I was going to say this is the answer, but I think you got that. Let's work on a rational function. The reason rational functions are a little bit harder is because they have vertical asymptotes on them a lot of the times. Not always, but often. And we just have to make sure we know how to work with those vertical asymptotes. So this will be g of x, example 2. G of x is 1 divided by x squared minus 9. Now, it's a rational function. Remember, rational functions are polynomial fractions. So the quotient of two polynomial functions. But when you think rational, you think ratio, fraction. If I wanted to, I could rewrite this function by factoring the denominator. I know that x squared minus 9 is the difference of two squares, which I can factor as x plus 3 times x minus 3. Now, you might want to note right away, we spent a lot of time in chapter 2 just looking at the domains of functions. In the last example, we didn't really need to think a whole lot about the domain because it was a polynomial, although I know the word domain came out of my mouth at least once when we were working on that problem. We didn't really write it down. It's just we just knew the domain was all real numbers. But in this case, we want to say that the domain of your function is all the values that don't include -3 or +3. I cannot have -3 or +3, otherwise my denominator will be equal to 0. So I can go from -infinity up to -3. I can go from -3 to +3, and then from 3 to infinity. But we have to exclude -3 and +3 from the domain. And because they make the denominator 0, and we can't actually cancel them out, these are vertical asymptotes on your graph. These are values that do not exist. So we have a vertical asymptote at x equals -3 and x equals +3. Remember, we're going to state this right now. Vertical asymptotes cannot represent critical numbers. So even though they're going to end up making your derivative 0 or not exist, we're still not going to call them critical numbers. All right, so first things first, we did that. Next, we're going to take g prime. Now, you can always use the quotient rule, or if you would like, you might just want to use the chain rule. Remember that I said that a lot of times it's easier to just use the chain rule if your numerator is a constant. If your numerator includes a variable, I'd use the quotient rule. But I'm going to rewrite g of x as x squared minus 9 to the -1st power. And now when we take its derivative, that'll make our job a little bit easier. Anytime I don't have to use the quotient rule, it's a little bit easier for me. So I'm going to bring the exponent down, rewrite the inside function, decrease the exponent by 1, and multiply by the derivative of the inside function. So remember that this uses the chain rule. I know I talked about how important the chain rule was, and I'm going to keep reiterating that because it is important. And I'm going to simplify my function g because I'm going to eventually need to solve this equation, and it's going to be a lot easier to solve the equation if it's written as a fraction. So if you're like, well, then maybe I should have used the quotient rule, maybe. That's always up to you. You always have that option available to you. So my g prime is going to be -2x divided by x squared minus 9 quantity squared. Okay. Now, to find the critical numbers, I'm looking for places where either the derivative does not exist or equals 0. So I'm going to say g prime of x equals 0 when the numerator equals 0. If you haven't done this in a while, I feel like this came up a few weeks ago and I can't remember why. But when we're dealing with rational expressions, when we're trying to figure out when the rational expression is equal to 0, we just need the numerator to be equal to 0. Now, if we're trying to figure out where it does not exist, we'll say that g prime does not exist when the denominator equals 0. So if the denominator if the denominator equals 0, we can't divide by 0. So that means we have a DNE situation, undefined. But if the numerator equals 0, well, 0 divided by a number gives us 0. That's why this works the way it does. So that's kind of the nice thing, is you don't have to get all crazy with like, oh, now I have to multiply both sides by, I mean, you can, if you set this equal to 0, multiply both sides of the equation by the denominator, and you'll get negative 2x equals 0, but you don't have to. You can just do it this way. So if it's rational and you're trying to figure out when it's equal to 0, set the numerator equal to 0. If you're trying to figure out where it does not exist, set the denominator equal to 0. Okay. Now, negative 2x equals 0. Divide both sides by negative 2, and you get x equals 0. This is going to be a critical number. Now, where g prime does not exist, that happens when x squared minus 9, quantity squared equals 0. Well, I think we can already see where this is going. Take the square root of both sides. You could solve this by factoring, or you could just solve it by using the square root property. Just remember that you need to apply the plus or minus sign. Now, these are vertical asymptotes. They are not critical numbers. So we still need to include them in the sign analysis. So I'm going to say I'm going to make a special note of this. We still include vertical asymptote values in the sign analysis. I mean, think about what happens at a vertical asymptote. You're going to have some sort of behavior to the left of it and some sort of behavior to the right, and you're going to need to know what that behavior is. So it might change on each side of the vertical asymptote, so we can't just act like it's not there. We still need to include it in the sign analysis, but it's not going to represent any sort of relative extrema. All right, so we have one critical number. I feel like it didn't get enough glory, so I'm going to put a little cloud around it. One critical number, but we have the two vertical asymptotes we need to include in the sign analysis. So let's go ahead and set that up now. I'm going to make my little number line here. I'm going to start out with my smallest value, which will be -3. I'm going to move up to my critical number at x equals 0. And then the last value I need to look at is x equals +3. Now, you might just even want to say it again. I know this is like the 4th time I've said this, but you might want to just note on these right now that they're vertical asymptotes so that you don't get confused later on, because there's a lot going on here. All right, so we have this now. What we're going to do is choose test points. So we're going to test a value on the left of x equals -3. So maybe I'll say that we're going to test x equals -4, x equals -1. I mean, you can choose any value between -3 and 0. X equals +1, and then maybe x equals 4. So we're going to test these values. We're going to get values for the derivative at the test points and determine what's happening to the behavior of the graph on these intervals. So I'm going to put this in my calculator, but essentially I'm looking for f prime of -4, f prime of -1, f prime of positive 1 and f prime of 4. And I'm going to figure out, is it negative or positive? And then we'll be able to determine here what's going on with the behavior of our graph. Okay, now I'm going to enter the derivative into my graphing calculator. Move this up for a second. Be careful when you enter these in your calculator. I can't tell you how many times I've seen students get these wrong because they enter them into their calculator incorrectly. Your derivative is, oh, you know, I knew as soon as I called this function g, I knew I was going to have regrets. I'm calling it f again down here. You know what I mean. But either way, negative 2x divided by, in parentheses, x squared minus 9 quantity squared. Now, in this case, the numerator just has one term. If it had two terms, you better make sure you put parentheses around it. When in doubt, use parentheses. So that's my derivative. Let's go ahead and go to the table. I'm going to look at 4 different test points, -4, -1, 1, and 4. Those were the test values that we chose. Going back to our sign analysis. Now I got to switch these F's back to G's. I'm sorry. Listen, I'm not completely infallible. I will call every function F if given the chance. I'm very sorry. I need to be better about that. They're definitely G. And I know you know what I mean, but I don't want you to be like, wait, it says G. She wrote F. That's the last thing we need, is to add confusion to a calculus lecture. Let's just make sure we know what we're doing. Okay, there. All right, the derivative evaluated at -4 is positive. So it's like 0.1633. I'm not so concerned about the value of the number. I just want to make sure we have the sign correct. At -1, we have 0.0313. At +1, we have -0.031. And at 4, we have -0.163. So now we can make some conclusions. When the slope of the tangent lines are positive, I know the graph is increasing. 0.0313 is positive. At 1, we have a negative value. And now at 4, we also have a negative value. Now, the vertical asymptotes are here. We usually denote those on a graph with dashed lines. If you want to do that, that's fine. This sort of just gives you a mini visual of what's happening on your graph. And this kind of breaks it up. So you know that the graph was increasing on the left of that vertical asymptote. It's probably just going to increase to infinity, and then it's going to pick back up again and start to increase again on the next interval. Now, the interesting thing that we're going to be looking at is what's happening at the critical number. So the critical number is x equals 0. And you're seeing now that's not a vertical asymptote. We have that the slopes of the tangent lines change from positive to negative at that point. So we can say that we have a relative maximum at 0, f of 0. So whatever that is, it's going to level out right there. And then again, we're decreasing and decreasing. So let's go ahead and make some conclusions based off our sign analysis. We're at that point. So I can say that this function is increasing, or I'll say g is increasing on, well, I know it's increasing from -infinity up to the vertical asymptote at -3. So I'm reading this from left to right now when I set up these intervals. -infinity to -3, And remember, it's not increasing on -3. It's a vertical asymptote. You cannot be increasing on that value. But you pick it back up again and say that it's increasing from -3 all the way up to 0. And this is where you get that hill that occurs. You're at the top of the hill when you're at x equals 0. Now we could say that g is decreasing. Oh, this is the only example I'm doing on this page, by the way. So if you're like, oh my gosh, how much space am I using up? Sorry, you can start writing bigger now. G is decreasing on the interval from 0 to 3. And then from 3 to infinity after you hit that vertical asymptote at 3. Now we can say something about the relative or local maximum. Call it whatever you want. It's occurring at 0, f of 0. And if you want to just go ahead and find f of 0, we have a little bit of space to work with. Oh, I called it f again. Guys, you know what I meant. It's not f, it's g. G of 0. I'm never calling another function g again as long as I live. Okay, g of 0. G of 0, well, my original function g was 1 over x squared minus 9. So this is going to be 1 over 0 squared minus 9, which is -1/9. So I can say I have a relative or local maximum at 0 and -1/9. I think we should look at this graph on our calculators. What's the point of finding all this cool information if we can't be like, wait, look, you can see it on the graph. This is awesome. We're going to graph the original function. We currently had the derivative in there, but let's go ahead and graph the original. So this will be 1 divided by, in parentheses, x squared, whoops, x squared minus 9. So there's your function. I'm going to just zoom 6 and see what happens. Now, up until you hit this vertical asymptote at 3, you can see it appearing on your graph. I mean, it doesn't show up as an asymptote, but you can see that the graph doesn't have any function values there. Your graph is increasing up to the asymptote. And then from -3 to 0, the graph is again increasing. And then you hit this relative max at 0, and then it starts to go down, just like what our sign analysis predicted. So it starts to decrease, and then it hits this vertical asymptote at 3, and then it starts to decrease again. So you're seeing this behavior exactly matches what's going on with your graph. Now your relative max, I know on the graph it looks like it's at 0, 0, but remember, -1/9 is a really small value. So if you were actually to go to your table and evaluate the function at 0, you will find that it's -1/9. That's just the decimal approximation. So it's not actually at 0, even though it looks like it's at 0 on your graph. It is not. Remember, you could always go to second calculate and find the maximum, number 4. Move to the left, enter, move to the right, enter, enter again, and it will give you that maximum value at like -0.111, which is just -1/9. So that's really cool. Excellent. So all the really important information that we needed, the answer to the question is in this box. These are the intervals where the function's increasing, decreasing, and we found the relative or local extrema, which is so much information, so much. All right, we're going to do one more type of example, and then we're going to look at how the graph of a function is related to the graph of its derivative, which is also really cool. All right, so the next example will be a radical function. So you're going to see in these examples, especially as we're working here in chapter 4, you're going to mostly be looking at polynomials, rationals, and radicals. Now, sometimes your radical functions will be written with radical notation, and sometimes they'll be written with rational exponents, but they're still both considered to be radical functions. This one that I'm going to give you next is written with a radical. Example 3, and this we'll call f of x. No more g's for this girl, not today. Got to be feeling especially brave if I'm going to call a function g. All right, so this is f of x is x times the square root of x minus 8. Now, maybe you're looking at this and you're automatically thinking back to what you learned about domain. And that's awesome if you are, because we do need to consider the domain of this function. X can't just take on any old value. We need to make sure that what's under the radical is at least greater than or equal to 0. So let's look at the domain first. That's always a good idea because you don't want to be choosing values that aren't in the domain. That will lead to lots of confusion. We need to force x minus 8, which is the radicand, to be positive or equal to 0. Now I can say that x is greater than or equal to 8 when I add 8 to both sides. So that means that only values of x that are 8 or greater than 8 are going to work for this function. If you choose a value that's less than 8, you're going to get something that's undefined. Like 7 minus 8 is -1. You can't take the square root of -1 and get a real number. It's not going to show up on your graph. So we're going to only choose values in the interval that follow this domain. So this is very, very, very important when you're looking at any sort of radical function, or in the last example, we were looking at a rational function that had vertical asymptotes. Here you just have that the graph doesn't exist for a whole plethora, an infinite number of values. So let's go ahead and use the first derivative test. The first thing we need to do to use the first derivative test is take the derivative. This derivative is going to need the product rule and the chain rule. F prime of x needs product and chain rule, because the inside function is not just x, it's x minus 8. So we will go ahead and find this derivative. If you would like, you might want to rewrite this notation to be x times x minus 8 to the 1/2 power. We'll make your derivative a little bit easier to see with that rational exponent. So f prime of x is going to be, f will be x. I know. See, now I called the function f, and I'm again having regrets because now I can't use f and g with my product rule. But you know what? We should be good with the product rule by now. I shouldn't have to keep labeling parts of my function. F prime g plus f g prime. So g prime is where the chain rule comes in. I'm going to bring down the 1/2, rewrite the inside function, decrease the exponent by 1, and multiply by the derivative of the inside function. So this is where the chain rule comes in. Okay, now we're going to rewrite this because I have to do some work with this. Remember that the whole idea here is we need to find places where the first derivative either does not exist or equals 0. It's going to be a little bit hard to do that with the function written like this. So let's rewrite it. You might want to use radical notation here. You might find it easier to work with algebraically, but I will leave that up to you. I usually do that when I solve equations, but I guess it sort of depends on the circumstances. Okay, now I'm going to just simplify this a little bit. The 2 is going to go into the denominator. The x will stay in the numerator, and the negative exponent, I'm going to move into the denominator as a positive exponent. So I've got x divided by twice the square root of x minus 8. Now, I can't force you to use any particular method when you're solving an equation, but if I need to go ahead and set the derivative equal to 0, it's going to be easiest if I can evaluate this the way I did the last example. Remember, with the last example, we had a rational expression and we said, all right, well, when the numerator equals 0, the derivative equals 0. When the denominator equals 0, the derivative does not exist. If you can turn your derivative into one fraction, you're going to make life a lot easier on yourself. So I'm going to write a note for you here that says combine into one fraction. Or let's see, write as one fraction, something like that. That's going to help you immensely. And you might resist at first, but you'll realize that this is actually going to make your life a lot easier. So I'm going to multiply this first term by the LCD, which is twice the square root of x minus 8 over itself. And then I'm going to add that to the term that we currently have. You can even do that if you want. So you're just taking this first term, which is technically this value, and you're multiplying it by the LCD over itself. And remember, this is just a special name for 1. So this is what you're introducing so that you can get this combined as one fraction. Okay. So let's simplify this out. The square root of x minus 8 times itself is just x minus 8. The square root of a quantity squared is just what's under the radical. So we can say now that f prime of x is twice x minus 8 plus x, and then the denominator is twice the square root of x minus 8. If you need to pause and look at that again, that's fine. But I'm going to simplify this. So you have 2x minus 16 plus x divided by twice the square root of x minus 8. And then we'll simplify one more time to write this as 3x minus 16 over twice the square root of x minus 8. This is where all that algebra you've learned in your lives is going to be really helpful to you. I want to figure out where the first derivative is equal to 0, and I want to find out where the first derivative does not exist. So what I'm going to do here is to find my critical numbers. I'm going to say it must be the case then that my numerator equals 0 means that f prime of x equals 0. And if my denominator equals 0, then my first derivative does not exist. Okay, so I have x equals 16/3. And then for my if f prime of x does not exist situation, I have that the denominator equals 0. So that means that I can multiply both sides by 2. And then in this case, I would multiply or square both sides and get x equals 8. Now, we have two values here. One of them is going to be a critical number for us. The other is not. Actually, and I'm even a little bit doubtful about one of them. The first one is 16/3. And if you were to rewrite this as a mixed number, you would get 5 1/3, or you put it into your calculator and it's like 5.3. Yeah, it's not in the domain. So if you didn't take the domain of your function and you took this as a critical number, you'd be like, all right, well, let's, put this in our sign analysis. Your calculator would spit out a bunch of like errors at you when you tried to evaluate it. And you'd be like, I don't get it. What's happening? I'm so confused. I'm just trying to alleviate that confusion that you're inevitably going to have if that happens. So make sure that we understand that this is not in the domain of f, so it's not a critical number. I'll put a little cloud around it. I'm running out of space here. So it's not a critical number. X equals 8 is an endpoint. So I would not consider that to be a critical number either. So X equals 8 is definitely a value that is going to go into our interval. It has to, but it can't be a critical number because it's an endpoint. Remember that critical numbers are going to occur when you have some sort of local neighborhood around them. Well, if this is the first value that could possibly exist in your domain, that means that there are no values to the left of 8 that are even included. So we're going to use this, but it's not a critical number because it's the endpoint of your interval. Now, if you're thinking like, oh, well, okay, cool, we have no critical numbers, I don't have any work to do here. That's not true, because you still need to determine what this graph is doing on its domain. Is it increasing or is it decreasing? Now, we know we can't possibly have any relative extrema. We can't have any relative extrema because we don't have any critical numbers. No critical numbers means no relative extrema. Wow. Dropping pens everywhere. No critical numbers means no relative extrema. It's very important. And it's very subtle, where there's all this information that you think you have, but you're like, wait, do I even have any information? Okay. But we're going to set up a sign analysis just covering the whole interval from 8 to infinity. Our domain is any value of x that's greater than or equal to 8. We're going to start our sign analysis at 8 and just go up to infinity. So it looks like this. It starts at 8. It moves its way up towards infinity. You're going to pick a test value in there. So maybe you're going to say, let's test, I don't know, x equals 9, something small. And we'll take the derivative and evaluate it at 9. Now, you only have one value here to evaluate. It might take longer for you to put this derivative into your calculator than just pop in a 9. So I'm just going to evaluate f prime of 9 using the definition of f prime of x. So f prime of 9 is going to be 3 times 9, which is 27 minus 16, divided by twice the square root of 9 minus 8, which is the square root of 1. 27 minus 16 is 11. Divided by 2, we have 11 halves. That means that your derivative is positive on this interval. 11 halves is definitely greater than 0. So that means that on this interval, your function is increasing. I need to make a conclusion somewhere. Let's make it right here underneath this little note. We would say f is increasing on its entire domain, or you can say that f is increasing, we should be more specific, on 8 to infinity. Now, I have seen some books and I've seen some instructors who say that this is increasing on 8 inclusive to infinity. Using a bracket on 8. I know it's not that big of a deal and maybe you wouldn't have even thought about it, but we can't actually be increasing at 8 because that is your endpoint. So in order to, I mean, I wouldn't consider that a place where we would be increasing. I always think like, how can you be increasing at an endpoint? That's the start of your interval. I would leave this open, but your book, I want to say I even checked this. And your book also left it open. Why do I not remember this though? I would leave it open though, from 8 to infinity. In order to be increasing, we usually say that the derivative has to be positive on both sides. But how can your derivative be positive left of 8? It cannot be. So I would leave this open. Okay. So you saw 3 different types of functions where we did a sign analysis using the first derivative test. Now, the last thing we're going to do in this section is talk about how the graph of a function relates to the graph of its derivative. So this is actually pretty cool. If you're like, oh my gosh, I've been sitting here forever doing this, this is a good stopping point if you want to come back and finish the video later. But I don't like to tell students to do that either, because I'm always worried that they're not going to come back and finish it later. So that's on you. Let f of x be the graph at the right. Where is f prime positive, negative, and 0? Well, f prime is going to be positive, negative, and 0 related to where those critical numbers are and what's happening to the slopes in between those critical numbers. So if you were to pick out something like, I don't know, maybe a critical number might be here at 1/4. Maybe you would have a critical number right here. I don't know what that would be, like 3/4 maybe. Let's call it 3/4. And then, oh, you know what, instead of making, doesn't really make sense to do that. I only did that for this one. You'd have the slope of the tangent line being 0. And then here at the bottom, you also have the slope of the tangent line being 0. So I don't know, maybe that's like 2 1/4. We'll call it 9/4. See, now this is going to drive me crazy. I hope you're all doing this in pencil. Excellent. So we have these places where we can see that the slope of the tangent line is 0. We have the bottom, a little bit of a valley here. Then you have a hill. Then you have another valley. So what's happening is we need to focus on what's going on the left, to the left of your first critical number, to the right of your last one, and in between your critical numbers. So of course, as we move to the values that are approaching x equals 1/4, the slopes of your tangent lines are negative. So I could make this statement that f prime of x is less than 0 on the interval from negative infinity to about positive 1/4. And I could say the same thing. I mean, they would be increasing from about 1/4. It's negative 1/4. Negative 1/4. Sorry. And then we could say the same thing to the right of 3/4. I could pick any test point inside here, and you would get that the slopes of the tangent lines were decreasing. So that is also going to be true from 3/4 to 9/4. We might also just want to state that f prime of x equals 0. We already picked these points out about. I mean, we're just eyeballing it. They're not really labeled per se. And then as far as values where the function would be increasing, I'm looking at values that are between negative 1/4 and 3/4. And then again, from about 9/4 to infinity. I think we are getting a really good sense now for what that means and how it works. Now, if we know that this is the graph of f, we're being told let f of x be the graph at the right. So this is f of x. We can pick out some information that we know will help us to look at the graph of f prime. So I know that f prime has to be less than 0 on these intervals and greater than 0 on these intervals. So that will give us some information about what the actual graph looks like. So I know that at some point here, until I hit this value where my slope of the tangent line is 0, the graph of the derivative has to be somewhere down here because it has to be negative. And then once my graph of f starts to increase, the derivative is positive. So the graph of the derivative would lie above the x-axis. So we're going to formalize what all of this actually means, but I think that would be very useful. And then we'll look at some examples. All right, so graphs of functions and their derivatives. In general, to determine where an x value will be on the graph of the derivative function, look at the slope of the tangent line. At that x value on f of x. So specifically, where f of x has local extrema or mins and maxes, well, we might have two different things happening. It could be that the slopes of the tangent lines are 0, or it could be that they do not exist. So this leads us back to the very first thing we were talking about in this section. We had the graph where we had slopes of the tangent lines being 0 with local extrema. And then we had another graph with a sharp point where the slopes of the tangent lines did not exist, but we still had a minimum or a maximum value. On the graph of f prime of x, this is going to look like two different things. If the slope of the tangent line is 0 on f prime of x, this is going to represent x-intercepts. And if we have that the derivative does not exist on the graph of f prime, this will look like 0 or a vertical asymptote. Now, if your graph of f of x is increasing, that means that the slopes of the tangent lines are positive. And if the slopes of your tangent lines are positive, then the graph of f prime in this situation is going to lie above the x-axis. If it's decreasing, if f of x is decreasing, the slopes of the tangent lines are negative. If the slopes of the tangent lines are negative, that means f prime is negative. That means the graph lies below the x-axis. If f of x is constant, that means that the slopes of the tangent lines are 0. If that's the case, then this will just represent sitting on the x-axis for your derivative graph. So we're going to look at a couple of examples and I'll get you out of here, I promise. I know there's so much to do in this section, but it's crucially important. There are fewer sections in this chapter, but they're kind of loaded. Example, here's a graph of a function f of x. Next to it is the graph of f of x, still in this reddish, brownish, rusty color. But the graph of f prime is also placed on the same axes. So your f prime graph is this greenish colored one. And your graph of f of x is the reddish one. Now, what you're seeing here, and I think sometimes this takes a minute to see, but it's really cool once you do see it. All right, so the graph of f is your reddish graph, right? The slopes of the tangent lines are negative up until you hit this point where you have this minimum value right about here. Once you get to this minimum value, the graph starts to increase. And then it increases up until about here. And then it decreases until you get to about here. What you're seeing with the graph of the derivative is that when the slopes of the tangent lines of f of x are negative, the graph of the derivative function contains negative values. Now, you'll see that right here, where you hit this minimum value, it corresponds to the point on the derivative graph where you have this x-intercept. So the graph of the derivative is 0 at that point. Now, once your function f of x starts to increase again, at this point, the values of f prime of x are positive. And notice that they're positive all the way up until they hit this point at 0, 0. And that's because When x equals 0, the slopes will start to decrease again to the right of that value. When the slopes of the tangent lines start to decrease in this interval from 0 up to whatever this point value is, the derivative is negative. And it's still, I know it looks like it's positive here, but it's not. It's still underneath the x-axis, so its values are negative. Up until you hit this value, once your graph hits that critical point, your graph of f, now all of a sudden the slopes of the tangent lines are positive again, and you see that the graph of f prime lies above the x-axis. So if you even wanted to look at it, like let's say I wanted to cover up part of the graph, if I only wanted to look at what happened above, well, I would know by looking at the graph of the derivative function that my graph is going to be having positive slopes from this point right here where you see this little red intersection mark all the way up to where you see this next intersection. So your graph, your red f of x is increasing. That means that your derivative graph lies above the x-axis. Same thing happens over here. When f is increasing, your derivative graph lies above the x-axis. You can do the same thing for below also. So I don't know. It's very cool. There's not like a ton that we're going to do, but it really is going to be important to be able to make the connections between those two graphs, f and f prime. All right, so now we're going to determine by looking at f and f prime. We're looking at two graphs. Neither one of them is labeled. You're going to determine which one's which. Now, you know that when you're looking at a polynomial function and you take its derivative, it actually decreases by a power. So that kind of will help you out. So if you're looking at this function, it looks like a parabola. The red one looks parabolic, whereas the green one is just linear. So it must be the case then that the green one is the simpler function. It's the derivative. The red one is the original function because it's got a higher degree. But you could also look at the slopes of the tangent lines to determine that. So you're noticing that on the red function, the slopes of the tangent lines are all negative until you get to this baseline point right here. And then once you get to this point, the slopes of the tangent lines are positive again. Well, at this point, their derivative changes from underneath the x-axis to above. So it must be the case that the parabolic shaped function is f of x. And then the green function, we would say, is f prime. So yeah, that won't always work, but it definitely works with polynomials. If it looks like you have, you know, something where you're decreasing in a degree, changing from something like x squared to just x. That should make sense. But again, you can always look at the slopes of the tangent lines and the values on the derivative graph to tell which one's which. Let me give you some more examples. Oh, I think we've hit the last page of notes. I think we should have a party now. We've made it through. Okay, so for this one, same idea. The original graph is the one that has more turning points. Its derivative is going to have fewer turning points. So in this case, the original graph is going to be the one that looks sort of like a cubic function. So I'm going to label that with f of x. And its derivative is going to go down by a degree and be f prime. Now, it could just be that this is like maybe you don't see the whole thing and that it's just like a trick, but it's not supposed to be a trick. Again, you can check. The slopes of the tangent lines are decreasing until you get to about here on this. Oh, I'm treating the red one like f of x again. Sorry, I got used to that from the last page. The slopes of the tangent lines are increasing until you get to be right about here, and then they decrease until right about here. And this is where you're seeing that the derivative function changes from negative to positive and vice versa. So if this is your function f, it's got the slope of the tangent line being 0 at this value, well, that's where your derivative graph has an x-intercept. Same idea here. You've got a slope of the tangent line being 0, well, your derivative has an x-intercept. X-intercepts. That's another way, you know, it's just the same, it's a different way of saying the same thing. But in this case, your graph is increasing. So up until that point, your derivative graph is going to be above the x-axis. When your graph of f starts to decrease in this interval, your graph of f prime will be below the x-axis. Your graph of f starts to increase again, your f prime graph will be above the x-axis. So lots of different ways of thinking about it, but basically the same idea. These get to be a little bit harder when you're looking at curves where it's really hard to tell, like, wait, which one has more turning points? Because you can't really see that in this case. But what you can do is you can look at the fact that for number 3, like, let's say I was looking at the red graph and I was thinking like, okay, maybe the red is the original function. Well, if that was the case, if the red graph was the original function, it would have slopes of the tangent lines always being negative. Sorry, I hope we don't have color issues, but I can say that for this graph, the slopes of the tangent lines are always negative. So this can't possibly be the original function, because that means that the derivative graph would always have to lie below the x-axis. But this graph, this green one, does not always lie below the x-axis. So we would have to say the opposite. So we would say that for the green function, in this case, this green function is always increasing on its entire domain. That means the slopes of tangent lines are always positive. So that means the other graph should always lie above the x-axis, which it does. So we would say that the red one always lies above the x-axis. So it must be the case then, it must be that the green function is your f of x, and that your red function is f prime. Okay, so this would be f prime of x, and then the green one is your f of x. Okay, and that's why if you can always just guess and be like, okay, like that's kind of how I started out. I guessed that the red function might be f, but it could not be because the slopes of the tangent lines were negative. That means the derivative would have to lie below the x-axis, and this graph doesn't. So this green graph can't possibly be the derivative graph to the red graph. So I had to switch it up then and say, okay, well, the green graph is always increasing. Therefore, the graph of the derivative should always be lying above the x-axis. It is. It doesn't matter that it's decreasing. That has nothing to do with this. It just matters that it lies above the x-axis. You can use the same kind of thinking for number 4. If you think that the red graph is the original, you have, in this case, that the slopes of the tangent lines are always positive. M's are always positive. And then it is true that on the green graph, the graph always lies above the x-axis. So we could say that, yes, it must be the case then that this red function is f of x, and the green function that's below is f prime of x. So we guessed right in that case. But let's say you guessed it wrong. You would have said, okay, well, I think that the green function is f. Well, it can't be, because the slopes of the tangent lines were negative. but the graph of f prime would have to be above the x-axis in that case, and that's not possible. So it must be that way. I got one more example for you. I know you're just like, oh, we thought we were done. Sorry, I should have given you a warning. We'll just do it real quick. Real quick. So I'm going to give you an absolute value graph. Looks like this. And then I'm going to give you what could be either the original or the derivative, and we'll have to decide which one's which. So this one will go this way. It's like a piecewise function that way. So you have to determine which one's the original and which one is the derivative. Well, again, the original is usually the one that's going to be slightly more complicated. And maybe you feel like these two horizontal legs are complicated, but I mean, turning point wise. The orange graph, this V-shaped graph, has a turning point in it. So I'm thinking that has to be f of x. And it is f of x. Think about the fact that the slopes of the tangent lines are decreasing until you hit the origin, or until you hit x equals 0. And then the derivative graph would be under the x-axis. Whereas once you get to the right of x equals 0, your V-shaped graph has positive slopes of tangent lines, and the derivative is lying above the x-axis here. So it must be the case that the V-shaped graph is your f of x, and your horizontal leg pieces are f prime of x. So we would say here that the m's are negative, and then your f prime is below the x-axis. And then here you would say that your m's are positive, and then your graph would lie above the x-axis versus below. Okay. All right. That's all I have to say about 4.1. This is going to take you a while to work through. Just remember, like I said, there are fewer sections in this chapter. So don't feel like, oh my gosh, I have like 10 super loaded sections to get through. I think it's, why do I think it's 5? I think it's 5 sections, but yes, it's 5 sections. And then some of the optimization stuff, I mean, we'll hit it, but it's not going to be like really thoroughly in depth. But I do definitely want to talk about how to optimize applications. So yeah, so these sections are going to be longer, but there are fewer of them. So really work hard on these. Like I said, these concepts will show up again in chapter 5 with new types of functions with exponential and log functions. So so there's a lot to do here, lots we're building up to, and check in on your calculator and kind of just compare the graphs and think about how cool it is that there's so much you can do without even having to use your calculator. Just, you know, checking it and making sure like, oh yeah, it all makes sense. Please go to the tutoring center if you have questions. Anybody in the tutoring center at ECC can help you. It's free. They have really cool hours. Go to the math lab if you want to work on your homework on WebAssign, any of those things. Utilize the resources that are taxpayer funded for you, and enjoy the rest of your day.